What's up guys, so today I'll be talking about electromagnetism, which is a progression of magnetism. I'll be doing this pretty quickly. Okay, so electromagnetism is broken down into two different hand gestures mainly. You have your right hand grip rule, which is something like that, and I've taught this in magnetism already. And we would have something new, which is a Fleming's left hand rule. So it's something like that. So it's like a physics gang sign. Okay, so let's look at current in a straight wire first. So current in a straight wire, when current flows through a wire, a magnetic field will be produced, and this applies to all sorts of wires. Okay, so the shape of the magnetic field really depends on the orientation of the wire, whether the wire is in a straight line or in a solenoid type. So what is solenoid? It is basically like electromagnets when the wire is curled around something. Yeah, that's a solenoid. Okay, so it follows our right hand grip rule. So the whatever's in a straight line, right, will be represented by your thumb. So if we look in this case, the straight wire, right, you will notice that the current will be represented by our thumb because it's moving in a straight line. Okay, so our fingers will be curling, and the finger curling will tell us the direction of the magnetic field. As you can see, for example, we look at this one, the current is moving upwards, right? So our fingers are curling in an anti-clockwise manner. So that's why you see our magnetic field lines are counterclockwise. Now that picture you previously saw can be also represented by a view like that. So this view would be viewed from the top. Okay, so you are looking at the wire from the top. So in this case scenario, you can see that it's represented by a circle with a dot. Okay, so what a circle with a dot means is that the wire is coming up towards you. Okay, so when the wire is coming up towards you, you notice that your fingers will be curled in anti-clockwise manner, right? And that's pretty much the same thing you see here. Okay, whereas for this one, your fingers are pointed downwards. So something like that. Okay, so you notice that your fingers will curl in a clockwise manner. So that's why the magnetic field lines are clockwise. Okay, you will notice that the gap between the magnetic field lines are getting wider and wider as well. So this is to show that as you get further and further and further away from the wire, right, the magnetic field strength is weaker. Okay, now we move on to the next portion, which is current in a solenoid. So now your right hand grip rule, right, the straight line, your thumb no longer represents current. Okay, in fact, your fingers that are curled now represents current because it's in this solenoid orientation. So in this solenoid orientation, you can see that current is moving in a direction like that. Okay, your current is actually going downwards. So what happens is your fingers would be curled down like that. Okay, just like your current. Okay, and then you notice that your thumb points that direction, right? And that will coincide with the direction of the magnetic field lines. Okay. Now there are three ways you can strengthen this magnetic field. The first way is by inserting a soft iron core into the solenoid. So basically inserting a soft iron core into a solenoid. That will turn it into an electromagnet, okay, and you will be able to concentrate the magnetic field lines or the flux inside this soft iron core. You can increase the number of coils or you can increase the current. Okay, now we move on to the next portion to talk about force on the conductor. Okay, now the main point about this portion is talking what happens when a current carrying conductor cuts magnetic field lines. Okay, so basically what happens when you put wires, right, when you have wires that carry current interfering with magnetic fields. So that's what we're talking about here. Okay, so you can look at this example. So what happens is when you put a current carrying conductor, right, basically a wire carrying current perpendicular to a magnetic field, as you can see here, there would be a force that will be exerted on the conductor. So in real life, if you would be looking at this scenario right now, what happens is this wire would be flying upwards. Okay, basically it would be forced upwards. Yeah. Okay, because it is traveling in a direction perpendicular to your magnetic field. So in a sense, it cuts the magnetic field. In this case scenario where we see, you notice that the current is actually traveling parallel to your magnetic field. So your magnetic field is going from north to south, always from north to south. but then you see your current here is along the magnetic field. Now in this case scenario, there will be no force experienced by the conductor because the current is not perpendicular to the magnetic field. The current is actually just parallel. Okay, so there will be no force experienced by the conducting wire. Okay, so this diagram is another view for you to see. So you see it is pretty much the same as what you see above here. So north to south, and then there's a current carrying wire here. So north to south, and then there's a current carrying wire over here. So the conductor will experience a force because you can see a 90-degree here. So basically this is where the 90-degree is. Yep. Okay, whereas for the other case scenario, over here, so you notice that the current is along the magnetic field. There is no 90-degree. I can't draw a 90-degree. There is no intersection at all. Yeah. So the conducting wire here will not experience any force. Okay, so we know there will be a force when a conducting wire cuts magnetic field, right? But that is not enough. Okay, what we need to know is the exact direction in which this current carrying conductor will go. Okay, so we need to know which direction will this thing head towards, and that's where our Fleming's left hand rule comes into play. Okay, left hand rule. Okay, so if we were to look at this example here, okay, so we look at this example and we can try it. Okay, so let's take a look. Yep. So current is represented by your middle finger. Okay, current is represented by your middle finger. Magnetic field is represented by your index finger. So basically magnetic field lines are represented by your index finger, and your thumb would tell you the force that is experienced, the direction of the force that is experienced by the conductor. Okay, so for this example we look here, current is represented by your middle finger, so like that, and then you know that your flux lines always go from north to south, so your finger point upwards, and then you notice that your thumb is pointing towards you, right? And that's why your force is pointing outwards. Okay, so something like that. Okay, so I'll be providing a brief explanation as to why the wire will be pushed outwards. Okay, it's a very quick explanation. So you notice here, this is actually what's happening when you place your conducting wire in interfering magnetic field. Okay, so now we have a current. We are actually looking at it from the side. So you see the crosses here. Yeah, we are looking at it from the side. Okay, so the current is going towards you, and if you use your right hand grip rule, you will notice that your magnetic field lines are going in an anti-clockwise manner. Okay, so you'll notice that in this side, right, you can notice that their magnetic field lines are in the same direction, right? So when the magnetic field lines are in the same direction, that's okay. Okay, there's no problem with that. But when they are in the opposite direction, that's when the flux lines will start to bend. So it's something like repulsion. Okay, so there'll be repulsion on one side, and then there is nothing going on this side. So what's happening is that the lines on this side, this magnetic field lines is forced to bend somewhere else. Okay, and it bends in a way that looks like that. Okay, so it bends in a way such that it looks like that. So the field lines actually like that, but it bends to become like that. So when it bends like that, right, the field lines, the magnetic field lines will always want to straighten itself. So when you want to straighten itself, as it straightens itself, it's like a slingshot like that. Like, you know, a slingshot. Basically, this area wants to straighten, so it pushes the wire out. Okay, and the last part I'll be talking about is a DC motor. So this one is also quite important, but I'll be running through it very briefly because I've talked about it already. So you notice that this is a DC motor. So what happens is we are making use of Fleming's left hand rule here to show us how a motor works. Okay, so if you look, there are two portions to this motor actually. So one portion is the left side. So the left side. So you will use your left hand rule, and you'll notice that your current is going that way. Your magnetic field is going from north to south. So you realize that your thumb will point downwards. okay, and the current is going this way. So for this case, right, the current is reverse direction. So when the current is reversed in direction, your force will reverse in direction. So if this side is pointing downwards, this side will point upwards. So you notice that this will form a couple. Okay, we call this a couple force. Yeah, and then what happens is this will cause anti-clockwise rotation, and that's how your motor is formed. Okay, so important parts of a motor include the commutator. So the commutator will cause the rod to basically energize and de-energize at certain positions. So as you can see here, if I have a positive on one side and a negative on one side, as it rotates, right, okay, what happens is at the middle point, at this point, the contact point would be lost, and then the commutator will not be energized anymore, but then it will move on and then it will re-energize the other sides. I've talked about this in class, so I guess this will be just a quick revision. Okay, so yeah, for this part I will have to go through it soon in greater detail. Otherwise, other than that, I'm pretty much done for this chapter. So it's just a really quick chapter. I have not gone through it in detail. Okay, it's a pretty quick run through. I hope it helps you guys. Okay, yeah, and if you guys need any more chapters or any feedback for me, you guys can just let me know. Okay, thanks.